Okay, let's take a look at this problem. This is a group problem solving exercise, just like what we would have solved in class. What we're given here is that we have a 2-pound brick sliding down a smooth roof with a speed of 5 feet per second. So if I were to just highlight some of these locations, so the brick is initially on the roof, it's moving at 5 feet per second, and it's located at position A at this given moment, right here. The question asks us, based off the geometry and based off the information that's provided, what's the speed at B and what's the distance from the wall to where the brick strikes the ground and its speed at C. Now, we could solve this problem using what we learned in chapter 13, which is kinetics. The sum of forces is equal to the mass times the acceleration in any particular direction. But what we also recognize is that this is a problem that deals with velocity, distance, and ultimately force. Okay, and because it contains these three components, this is a great problem to solve using work and energy principle. Now we could solve it using sum of force equal to mass times acceleration, just like I said, but we're not asked to solve for the acceleration, and why solve for something that the problem's not asking us for? So let's use this work and energy principle. We can solve for it a lot faster and a lot easier. Okay, so what is given? What's given here is the weight of the block is 2-pound force. We also know that the block is moving at 5 feet per second at that given moment at A. So it's moving with an initial speed of 5 feet per second down the roof itself. Okay? So how do we proceed? Well, the work and energy principle says that the kinetic energy at some initial location plus the amount of work that's done from an initial location to a final location is equal to the final kinetic energy. And I'm using subscripts A and subscripts B because the question asks us, among other things, to find the speed that the brick is traveling at location B. The other thing it's asking for, by the way, is that distance D that is shown on the diagram here, the distance in the horizontal direction that the brick ends up landing at after it flies off of the surface of the roof itself. But first things first, let's solve for that speed at location B. Well, the speed at location B is dependent on the initial kinetic energy and the amount of work that's put into the block or done by the block from its initial position to its final position. And that's going to yield a kinetic energy at location B. So the kinetic energy, T, is always equal to 1/2 mv squared, where v is the speed of the object that's traveling at squared. Therefore, kinetic energy, remember, is always a positive value because we are positive people as well. So if we were to look at this block and draw a free body diagram for this block, there would be a normal force that keeps it on the surface itself, that prevents the block from accelerating down in towards the building. You would also have a weight force pointing directly downwards, like so. Okay? Well, recognize that this term, the sum of forces, or the sum of work, rather, from position A to position B, we know that work is a product of two things. It's the product of force and displacement, which we can call S, times cosine of theta, where cosine of theta is the angle between the direction that the force acts and the direction that the object is moving in. We know that it's moving down the slope. And so this angle theta here corresponds to the theta in this equation for cosine theta. Okay, it's the angle separating the force direction to the direction of the displacement. And we know from experience that this brick is going to be moving down the slope. S is pointing down the roof itself. So theta is the angle between the direction of the force application and s, the direction that the object is moving. Now there's two ways that we can consider this equation. We can say, well, it's the product of the component of the force in the direction of the displacement times the displacement. Or we can look at it in terms of s cosine theta times f, which is to say the component of the displacement in the direction that the force is acting. We can either project the force in the direction of the displacement, or we can project the displacement in the direction of the force. Now recognize that based off of the geometry of this problem, we know that the vertical height, the vertical distance from position A to position B is 15 feet. And we know that the weight is pointing in this downward direction, which corresponds to a total drop of 15 feet from A to B. The only other work that's being done in this problem, potentially, could be due to this normal force. But notice that the normal force and the direction of the displacement, s, are 90 degrees apart from one another. So the normal force does no work in this problem. The weight force, however, does do work in the downward direction, right? We can either project the weight component in the direction of the displacement or direction it's moving, or we can project the direction that it's moving in the direction that the weight is pointing. So if we were to take this s component and project it into the downward direction, we know that it's going to move 15 feet, again, I'll highlight this, in the downward direction to get from position A to position B. Why am I bringing this up? Because it makes the amount of work done by the weight force very easy to determine. The work done by the weight force is going to be equal to the magnitude of its weight times the distance that it travels in the direction that the weight force is pointing. If we go back to the free body diagram, the weight force is pointing directly downwards. It moves from position A to position B, which is a difference of 15 feet. Now this is a positive amount of work that's done by the weight because the weight is pointing downwards, as is the component of the displacement from position A to position B. It's moving down and to the right, but it's moving down 15 feet. The weight force is also pointing down. So this must be a positive amount of work that's done by the weight force. Therefore, this is 2-pound force times 15 feet. This is equal to 30-pound force feet. That's the amount of work that's done by the weight force. Remember, whenever we're talking about work, we need to associate each amount of work to a respective force. Work and force go hand in hand with one another. So the amount of work that's done by the weight force is 30-pound force feet. And as we said before, the amount of work done by that normal force is 0 because it is pointing 90 degrees at all times with respect to the direction that the object is moving. So the normal force does no work, the weight force does positive work. Okay, so if we go back to our work and energy principle, we said that TA plus the sum total of the amount of work done from position A to position B is equal to the kinetic energy at position B, 1/2 mVA squared, plus a sum total of work that's done from position A to position B that's only due to the weight force itself. That's 30-pound force feet is equal to 1/2 mVB squared. Now recognize that the only thing we don't know in this equation that's not provided for us is VB, which is precisely the value that this question is asking us to determine. So plugging in 1/2 mass of the brick is 2-pound force divided by 32.2 feet per second squared times its initial speed, 5 feet per second. We square that. Plus 30 pound force feet is equal to 1/2 the mass, 2 pound force divided by 32.2 feet per second squared, VB squared. One equation, one unknown. The units in this term, pound force per feet second squared, is slugs. The units here are going to be feet squared per second squared. So when we have slug feet per second squared times feet, we're left with units of pound force foot. We can always do this dimensional analysis. Pound force feet is the same unit that we have for our second term, pound force feet. And all things being equal, if VB is expressed in feet per second, this last term will also be in pound force feet. So a quick dimensional analysis shows us that we are adding apples and apples together. So we can punch this right into our calculator and solve for VB. And when we do, we find out that VB is equal to 31.48 feet per second. Okay, so that answers the first part, which is what is the speed at B? In order to do that, we had to project the distance, the direction of the displacement in the direction that the weight force was pointing. So we took this S component and we actually projected it downwards, and we knew that from location A to location B, the difference in the height, okay, that downward direction is 15 feet. So 15 feet times the magnitude of the weight, 2 pound force, that gave us 30 pound force feet. The second part of the problem asks us to determine what that distance D is that's shown in the diagram. It's the range, essentially, from location B to location C. How far in the X direction has the block flown? Well, at this point, we just turn to our understanding of kinematics, the study of motion for motion's sake, and we could solve this pretty easily. We recognize that xc is equal to xb plus vbx times the flight time from B to C. So if I want to put subscript B to C to be absolutely clear, I can do so just like this. This comes from our projectile motion problem, right? At this point, as soon as the block leaves location B, it feels one force, and that's the force due to gravity, and it starts to behave like a projectile, okay? So if we want to determine what xc is, okay, xc would correspond to that distance d. We plug that in. D is equal to the initial x position. Well, according to how we've set up our x and y coordinates, x of b is equal to 0, plus the initial speed in the x direction times the flight time. Now, we don't know offhand what the initial speed is in the x direction, but we do know that the speed at b, we just solved for it, is 31.48 feet per second. We know that when it leaves the roof at this location B, it's traveling down and to the right, and it was doing so according to a 3-4-5 triangle. Now, when I see a 3-4-5 triangle like so, I actually just choose to solve for this angle theta, okay? And if I solve for that angle theta, recognize that that's the same angle theta that exists here as well. So I don't know what VBX is immediately, but I can determine what it is from VB and that angle theta. VBX is going to be equal to VB cosine theta. Similarly, VBY is going to be equal to negative VB sine of theta. So I'll give you a minute to think about how I know that, VB sine theta and VB cosine theta. Okay? When I plug in this value for VB cosine theta for VBX into my top equation here, I find out that D is equal to 6.996 T BC. Okay? Theta, if you're unsure, is going to be your inverse tan of 3 over 4. Okay. So once we determine what theta is, we can plug it in for VBX. VBX is initial speed VB, 31.48, times cosine of theta, that angle that you just determined. So the relationship between the range d and the flight time is circled now in blue. Well, we need to know what the flight time is. So we turn to our y direction equations. And if y is positive upwards, as we tend to use, we say that y at c is equal to y at b plus vby times the flight time from b to c minus 1/2 gt squared, where t is also the flight time from b to c. The position at c is going to be equal to 0. The position at B is going to be a positive 30 feet. That's given to us in the diagram. I'm going to circle it over here. Plus VBY, that's just negative VB sine theta times TBC minus 1/2 32.2 feet per second squared TBC squared. We know what VB is. We solved for theta in the last slide. So the only unknown at this point is TBC. Using our quadratic formula, TBC turns out to be 0.899 seconds. This is the flight time. How much time does it take for the brick to move from location B to location C? TBC is the flight time to get from B to C. Going back to our equation circled in blue here, that relates the distance d with respect to time. D is equal to 6.996 TBC. 6.996 times 0.899 seconds. D turns out to be 22.6 feet. And that's it.